Thank you very much. Let me share my screen now. So
I can hand it over now.
Perfect. Well, thank you very much for that lovely introduction. I'm very excited to be here today. I think it's a great thing about causal inference that it spans so many different fields, mathematics, physics, computer science, psychology, cognition, and so forth. So I'm really excited that these types of events are kind of gaining more traction in the wider community. So super excited to be here today. So the talk that I'm going to give today, I'm really going to try and motivate all of the projects that I'm going to tell you about with some kind of real world examples that kind of set the scene and show you that some of this work is not just, deep and mathematical, but it has some way to be applied in the real world. And that's kind of why I love causality, right? Because it tells us something deep and philosophical, but at the same time, it tells us something useful. So I'm going to really try and stress that in today's talk. I know there's a kind of broad audience here today. So some of the slides in here I had adapted from a talk I gave at the Alan Turing Institute last month. So some of them get a bit mathematical, but don't worry if you see kind of equations that you don't understand or haven't seen before. I'm going to talk through what they all mean, what the intuition behind them is. So that shouldn't really be a barrier to kind of understanding here. So if you see any kind of crazy looking things, just feel free to disregard them and I'll try and guide everyone through it as best I can. Great. Okay, well, let me dive straight in with our kind of first motivating example. Okay, so early in 2020, some weird headlines started appearing around the world. So this is one from the Daily Mail, which in the UK is a kind of well-known tabloid newspaper. And the headline read as follows: so more evidence that smoking may cut the risk of coronavirus. So a review of 28 studies showed that the number of smokers among hospitalized patients is much lower than expected. And this kind of baffled experts, and experts thought this finding was kind of quite weird. And so as you would expect, this is quite a strange result, right? Smoking in principle damages your lungs. COVID attacks your lungs. Surely smoking would make you more at risk of getting COVID, not less. But the findings were irrefutable. If you smoked, the data said you were less at risk of contracting COVID-19. So should we take from this that we should all start smoking? Is that the type of decision we should make from seeing the correlation in this data? So let's kind of dive into how this data was generated in the first place. So at the start of the pandemic, there was a very kind of restricted testing policy in action because we didn't have that many tests. So only healthcare workers who, as a demographic, generally smoke less, and people with severe COVID, because they're the ones going to hospital, were tested in the first place. So this meant that smokers with no COVID symptoms were massively underrepresented in the observed data. And so an inference from this is that, of those people who were tested, the non-smokers are way more likely to have COVID than the smokers. And kind of this imbalance is what's kind of telling us that there's this correlation between smoking and reduced risk from COVID. Doesn't tell us anything about the underlying causal relationship between these two things. So if we were to kind of base any decision or action on the correlations that we saw from this data, such as how patients with or without COVID who smoke are treated, this would not have increased patient survival. It wouldn't have reduced our COVID risk. And so the take home from this example is that relying on correlations extracted from observational data can lead to embarrassing, costly, and in this instance, dangerous mistakes. And so to really overcome this and to make actionable decisions from data, we need to understand cause and effect. So how do we do this? I mean, this is quite a big kind of topic. How should we approach this? So the kind of gold standard to do this is to run a randomized control trial, or in the kind of tech industry, these things are called A/B tests, the exact same thing. And so this would in principle help us understand, the average causal effect of smoking on COVID and so forth. Because these things are randomized, they kind of cut any link to kind of any predisposed covariates that might make you more likely to smoke, less likely to get COVID, and so on. And so you can really ascertain from these things, this is what smoking would cause in terms of COVID. But much of the time, especially in this case, because we can't force people to smoke, it's not ethical, we can't run these types of randomized control trials. So at Spotify, it's still the case that, we run a lot of A/B tests, but there are certain types of A/B tests that we just can't run. They'd be too damaging to our user experience. So some examples would be, do app crashes cause users to churn, which means to kind of, not renew their Spotify subscription? We can't really force the app to crash for certain users and see what happens, because what's the point in doing that? If we think it's going to have a bad outcome, why do we force that on some people? Another one is, does podcast consumption cause users to stay with Spotify for longer? To really test that, we'd have to take podcast access away from a subset of our users in some sort of random fashion. We don't really want to damage their user experience in that way. So if we can't run these A/B tests, what can we do? So this is where causal inference comes in, and it kind of gives us the tools to, among other things, in some sense, simulate randomized control trials, at least given a certain set of assumptions that, may or may not be realistic given the situation at hand. But that's the promise of causal inference. You can simulate these things given these assumptions. But now what we've talked about thus far is only when there's one intervention, one action, one treatment kind of happening at once. So, smoking or not, people listening to podcasts or not. But things get really tricky when more than one action or treatment can occur at the same time. And so in many applications, as we saw, only a single intervention is possible at once. But in many other situations, multiple interventions concurrently are applied. So they happen kind of at the same time. So in medicine, for instance, patients that possess many comorbidities, I spelled that wrong there, may have to be simultaneously treated with multiple prescriptions, and all these prescriptions could interact with one another and so forth. And in computational advertising, for instance, people may be targeted by multiple campaigns in the same time window and so on. So how do you understand which one was the one that caused the user to retain, or at least how do you attribute the changes to these individual treatments that have happened at the same time, and moreover can interact with one another as well, like in the medicine example. And a really big example of this that we've all experienced in the last 2 years is during the pandemic, many interventions were applied at the same time. So, mask wearing, working from home, schools being closed, these weren't applied in isolation separately. They're all kind of applied at the same time or close to that kind of same time. So how do we understand the different effects that these individual things had on the eventual outcome if they all happened at once? How do we disentangle all their effects? So what do we do in this case, right? This is a more challenging problem. So before I state the first problem that we're going to talk about today, I'm going to define, from kind of first principles, what a causal model is, what Pearl's causal hierarchy is, and we can kind of go from those definitions into the actual problem we're going to talk about today. Okay, so causal models, what are they? So usually these things are represented by what's called a directed acyclic graph, or a DAG for short. And the reason it's acyclic is that, we expect cause to precede effect. There's some sort of notion of time. And so if there were loops in what's going on, it would feel like something you could cause yourself, which is a kind of strange phenomenon. So we have this directed nature going on. The arrows in this diagram denote causal effects. So the edge of the arrow is the cause, the tip of it is the effect. And you can kind of see what these arrows designate as what is causing what and so forth. So now, in addition to this, observed variables that cause each other, there are some unobserved things as well that go into this. And usually in the causal model framework, you assume that there are these noise terms which are hidden from us. So these are represented in green in this diagram here. And these noise distributions are kind of distributed according to something that we don't know about, we don't have access to. And the whole picture generates observations because there's a function that maps every parent to a given child. So a parent is just one of the causes, the child is one of the effects. And so what this means is that, say, for instance, node A in the graph is a deterministic function of its parent, which is C, which is the observed parent in the graph. And this noise term, U, which we don't have access to. And the reason why, we can talk about deterministic functions here, but still generate probability distributions is because we don't know what the distribution of the noise term is. And that kind of lack of knowledge translates into lack of knowledge about what value A might be, what value C might be, and so forth. So deterministic functions can still generate conditional distributions, joint distributions, and so forth. It's just that in a causal model, these joint distributions, these observations, probability distributions come from an underlying determinism. It's just that we lack knowledge about some aspect of it. So that's why we have these, uncertainties associated with things like this. But the cool thing is that we have these deterministic functions, and they allow us to do kind of more reasoning than we could by just looking at correlations. Okay, so we have causal models. And now let's talk about Pearl's causal hierarchy. So given a causal model, what type of things can we do with it? So Judea-Pearl kind of neatly categorized the different things we can do into these three different, he calls them layers of his causal hierarchy. So the first layer is just all about observation. So generating probability distributions. Given I observed A happen, what's the probability or the likelihood that B will happen? And then the next level, one level up from observations, is all about interventions. And this is all about, the layer at which A/B tests, randomized control trials live, because there we're kind of forcing into the model, changing some things. What would happen if we forced somebody to smoke and so forth? At the top layer are these things Pearl calls counterfactuals. So these, in a sense, are meant to be a proxy for the ability to imagine. You observe a given situation, you ask, okay, given I've observed this situation, what would have actually happened had some precondition been different? We'll get to counterfactuals later, a little later in today's talk, but we're going to dive a bit deeper into these kind of observations. So observations, as I say, just give you these joint distributions. I'm going to work with this classic example of smoking and lung cancer and so forth. So here you can have, a variable that says if you smoke or not, then you can have a variable that says if you have cancer or some sort of health condition or not. But there can be unobserved things, such as, for instance, your genetic predisposition to various things that are kind of, at least on the kind of coarse grain level, hidden from us, but they could influence both your smoking and developing cancer in the first place. So at the first level, we can talk about these joint distributions. Given that I saw you smoke, what's the likelihood you have cancer? The next level, it's all about intervention. So it's saying, okay, what if I forced you to smoke? What would happen then? And so in this case, you can see the arrow between the genetic predisposition to smoking has been taken away from the graph. Why is this? Well, we've reached in and we've forced smoking to take on a certain value independent of anything else in the graph. Thus, when we do this, any cause from some sort of confounding factor or previous factor is discounted because we're reaching in and changing it ourselves. And so Pearl introduced a cool bit of notation to illustrate this. He called this the do conditional. So that's why there's this little kind of operator that says do on the right-hand side of the conditional symbol there. And this, in a sense, is kind of simulating what happens in a randomized control trial, because by randomizing things, you're, again, discounting the influence of these genetic or predisposition factors on the eventual outcome. Okay, so given that we've got that set up, I want to first kind of clear up a slight bit of kind of notation around what learning means, what reasoning means in this hierarchy. And this will kind of set up what we're going to talk about later. So first of all, learning here refers to the process of determining the correct causal parameters, the correct causal model. And by correct, what I actually mean is that given this model that we've learned, if I do inference or if I reason with it in some way, these kind of the correct definition here is when I return the correct answer for reasoning or doing inference on this model. And what's interesting about Pearl's causal hierarchy is that different levels have different definitions of correct, because each level asks a different type of question. So the reasoning we do at each level is slightly different. And so by doing these extra kind of steps, we impose more constraints on what we mean by a correct causal model or correct learning process. And so as we move up from observation to intervention to counterfactuals, what happens is we're imposing more and more constraints because reasoning gets more and more nuanced as we move up. So this adds more and more constraints on the learning kind of process. So you can think of learning as somehow like constrained by the type of reasoning you want to do. And that is determined by the level of Pearl's causal hierarchy that you're at. If you've got the correct model at one level, that means that if you go to one level lower, you still have the correct model. You can answer all the questions correctly. But if you have a correct causal model at one level, and you want to go one level higher, if you want to go from observations to interventions, it's not necessarily the case that the correct model at level 1 is the correct model at level 2. So this is what we mean by when we kind of say reasoning constrains the learning process. But that's just a kind of quick aside to kind of link, let's say, with the theme of today's talk. So given that we have all this, what's the first problem that we're going to try and address in today's talk? So this is the one that I kind of motivated earlier, right? We have many actions going on simultaneously, and we've observed them, happening at once. And what we want to do from this is we want to disentangle them and learn their individual contribution. So how do we attribute a change among all the different actions that happened, and they could have happened simultaneously? And so the idea here is we need to learn, or in the kind of parlance of causal inference, to identify what's called the conditional average treatment effects given joint intervention. So just to kind of highlight that, what we're given is just observations and joint interventional data. So two or more actions happening at once. And what we want to do from this type of data is find, okay, can we learn the individual kind of interaction from a single action? How do we say, oh, we've seen that we've applied these both actions at the same time. What would have happened had we just applied one? So that's the kind of problem that we're trying to deal with today, in this kind of disentangling of interacting causal treatments. Okay, so one quick note on what identifiability or learning means here. So a quantity is going to be called identifiable from a specific type of data if every model that agrees on that data, i.e. when making predictions from that data, has the same kind of value for the quantity that we care about. And kind of what this means is that if two models agree on the data, but not on the quantity we care about, then it's not identifiable from that data. That data isn't enough to tell us uniquely what that quantity is. And so what we're going to do now on the next kind of slide is produce two models that produce the same data that we care about. So observations and joint interventions, but yet we're going to show that both models have different predictions for the individual treatments, even though they agree on the joint treatments at the same time. And that tells us that we need more constraints on our kind of data generating process in order to learn or disentangle the effects of two simultaneous treatments. Okay, so again, this is a slide, there's a bit of maths on it. We don't really kind of care about that too much, but the basic idea is on the top of this kind of slide are the two models that I kind of talked about in the previous slide. And you can kind of see that X1 in both models looks the exact same. You can also see that Y in both models looks the exact same. X2 is what is going to look different in this model. But what's interesting in that in model M, X will depend on X, so X2 will depend on X1. So if I were to reach in and force or intervene on X1, change its value, then X2 would change. But in model M prime, which is the second one here, if I would reach in and change X1, X2 is not going to change because it does not depend on X1. But what's interesting is that when I just look at the observations coming from this model, X2 is the exact same in both models. And this is because X1 here is equal to U1. When you stick that in to X2, I get X2 is just U1 multiplied by U2. But these things are just binary digits. They're just 0 or 1. And moreover, I'm stipulating that they're all perfectly correlated. So when you have two bits or two binary digits that are perfectly correlated, it just means that the same bit. So they're either both 0 or they're both 1, which means that they're just 0 or 1. And so at this level, what this tells us is that X2 is actually just following U2 in both models. And so observationally, everything looks the same. Moreover, when I intervene on X1 and X2 at the same time, Y here, which depends on X1 and X2 in the same way, will change in the same way for both models. However, yes, please, if there's questions. Are there questions or? Grant, I will keep going. So
you can continue, Ciarán.
That's great. So in this case, joint interventions are the exact same. Both models make the same prediction. They also make the same prediction for the correlations, but the individual interventions, so if I just change X1 on its own without changing X2, both models disagree. They give this different answers. And so this tells us that even if we have both models constrained to have the same joint distributions, even if we have both models constrained to give the same joint interventions, it doesn't tell us that both models have to have the same single interventions. And so the quantity that we care about, learning the individual effects of all the treatments, you know, in COVID, if everyone's wearing a mask and staying home and kids are not going to school, which is the one that kind of reduced the COVID risk? Or at least how can we say how each individual action reduced the COVID risk on its own? Well, this is telling us that without further constraints, we can't do that. So that's a kind of interesting result, perhaps, from this kind of point of view. However, the question is, how can we identify this thing? What extra constraints do we need to provide in order to be guaranteed that we can learn the individual effects of these interactions? Well, so this is the kind of theorem that we've kind of proved in this case, which tells us that for a certain type of causal model, this is possible. So the certain type here is a model where each kind of treatment, so treatments here in this picture, this DAG, are X's, the outcome is Y. There might be some unobserved confounders influencing both the treatments and the outcome, which is U in this model. There might be some observed confounders influencing the treatments and the outcome, which is C in this model. And we're stipulating that if the function, the way Y depends on all the treatments and the kind of confounders here, looks like it does in the statement of this theorem. So, you know, all the X's can interact with all of the observed confounders to produce Y, but we have to add in the effect of the unobserved confounders. And so this is called an additive noise model, in that any unobserved things can influence the outcome, but they have to influence it in an additive way. And what's happening here is that all of these kind of things can interact. It's still, you know, a non-trivial model, but we've separated out, in a sense, the interaction and the influence from the unobserved part into a kind of structurally manageable kind of way. And so it was this lack of additivity in the previous example, which is what made things hard to do, because we couldn't kind of wash out the contributions coming from the unobserved things from the actual causal factors in the actual model. Whereas here we've kind of separated them out, but we've separated them out in a somewhat justifiable way, right? Because what's actually going on here is it's saying, okay, there can be still interactions that we don't observe. They just have to kind of change the outcome in an additive fashion. So there are kind of many situations in the real world where data has been seen to follow this pattern. So it's not an unreasonable assumption. So one big assumption we have made is that we've stipulated that the observed confounders, which is C, and the unobserved confounders have to be independent of one another. They can't be correlated, they can't interact. And so when you allow for an arbitrary interaction between them, the theorem no longer holds. And so this is perhaps a bigger assumption going into the model. There are various ways to relax it by kind of stipulating certain types of kind of interactions between the observed and the unobserved confounder. But usually in a causal model, one stipulates that most of the confounders are independent anyway, so perhaps it's not an additional, too big of an additional assumption. So you might also wonder, are there other ways we can adapt the theorem, change the model here, but still be guaranteed that we can learn something? And so indeed, you can do this. So one other assumption here is that the treatments themselves, while they can be correlated and they can interact due to the confounding influences, and also through the way they functionally give rise to Y, there's no causal interaction between these treatments on their own. So you might ask, okay, if we introduce a causal interaction, how does that change the statement of our theorem? And so it turns out in this case that you can still identify things, but you can't learn all of the individual treatments. You have to only learn a subset of them. And the subset you can learn are the ones which are the effects of the treatment causing them. So in this case, we could perhaps learn and disentangle the effect of X2 on Y, but we couldn't learn and disentangle the effect of X1 on its own. And so that's the kind of one extra statement. So to kind of go over all those different cases, here's a kind of brief schematic. So on the first DAG on the left, what we see going on here is because X1 has a causal influence on X2, the only thing we can reliably learn in every case is the effect of X2. So if we observe X1 and X2 both being applied to Y, we can learn the effect of X2 on its own. The same for the second DAG here. But in the third DAG, because there's no kind of causal interaction between X1 and X2, if we observe an intervention involving both X1 and X2 at the same time, we can disentangle that effect to learn the individual components of each, which is kind of the statement of our main theorem. Okay, so given the statement of our theorem, we had this kind of additivity structure, and it turns out that you can use this structure to create a learning algorithm, which can figure out what the structural equations, the equations underlying our causal model are, and moreover can learn the distribution over the unobserved things, these unobserved confounders that we have. And the way in which we do this is we employ what's called an expectation maximization style algorithm, where in one step, we improve our estimate of the function while holding the distribution over the unobserved things fixed. The next step, we hold the function fixed and we update our knowledge about the unobserved distribution, and we go on through this iteration style until we get to a kind of local minima in this case. And that gives us some good results. And so you can check the paper for the kind of full results, how we set these things out. There's some nice experiments in there where we check this out on real world data and show that indeed it does allow us to disentangle the effects of various treatments. So we applied it to a stroke trial where there was many dosages of treatments applied simultaneously, and we were able to learn the individual contribution of each kind of dosage level of each treatment in that case. But if you're interested, you can kind of dive into the paper. We presented it at one of the NeurIPS workshops. It's under submission somewhere else, and it'll be on the archive in a little bit, fingers crossed. Cool, so that's the kind of setup for that kind of first problem that I want to talk about. But you all might be wondering kind of what's in this for Spotify, right? How do we apply these types of techniques at a big tech company that's all about people enjoying music? Well, there's a range of kind of examples. So two of them are as follows. So there are a range of kind of playlists and albums and podcasts that are all recommended to a user at a given time. But we might want to learn what the individual impact of each one is so that we can figure out, okay, for this user, they might like podcasts way more than music. And so we might then update our recommendations so we're serving them the content they care about. And because we serve everything kind of at once on this homepage, we want to figure out what the individual contribution is so we can kind of give them the thing they really want. Another example is, there are a collection of actions that an artist can take to build their career, to improve their fan base and kind of so on. And they might do these simultaneously, right? Their music might go into playlists, they might try and promote their music on various other kind of ways and so forth. But which one is having the biggest effect for them? And for different artists, the different actions can have different effects. So we need to, on an individual artist level, figure out how to disentangle all these things. So we can say to an artist, well, you did this, it had this impact. You can do these two things at once and that'll have better impact on both, and kind of so on. So we can make the right type of decisions for an artist that kind of get the most out of Spotify. And there's many, many more examples, but there's kind of a flavor of how we're kind of using this at the moment. Great. Okay, so now I'm going to go on to the next example. And this one is all going to be about the top layer of Pearl's causal hierarchy. So the last one was about the intervention layer. Now we're going to talk about the counterfactual layer and the ways in which questions at that level might be used in the real world. Okay, so here's our second motivational example. So diarrheal diseases are a kind of leading cause of disease and mortality in the developing world. And to reduce these types of diseases in children in particular, a local NGO in Kenya built protective cement structures around a randomly selected group of springs. Researchers from the Poverty Action Lab work with this NGO to estimate the average treatment effect of this intervention. Did it reduce diarrheal diseases on average across all these sites? Because this is, in a sense, a randomized controlled trial. So they found something really encouraging, that spring protection significantly reduces diarrhea for children under the age of 3 by about 25%. So that's great. I mean, one may have expected it maybe to have a bigger impact, but still having an effect. So that's kind of really good news. But the next question is, because a lot of kind of money is spent on all these types of interventions worldwide, we need to figure out how best we can use this limited resource to make the most good happen, the most impact. And so the question is, should we scale this intervention up? Should we put cement structures around every kind of well in Kenya and kind of in the wider third world? Because these things are expensive, we need to be certain it'll help as we expect it will. So to really answer this question, we need to answer the following thing. How likely is it that the negative outcome was caused by the exposure to diarrhea and not something else? So the question we really want to answer in this context is, given a child developed diarrhea after drinking water from an unprotected spring, would they have still developed it if they drank it from a protected spring? And the hope is that if this intervention works, within a really large number of cases, they would not have developed diarrhea had they drunk from the protected spring. But how do we answer this question? It seems like a really convoluted counterfactual, if they had, then they would type of question. So this is where the third level of Pearl's causal hierarchy comes in. This is where these types of questions sit. So counterfactuals in some sense are kind of what if questions, and they're really powerful in personalized decision making. So let's unpack this a little bit. So here's our kind of classic smoking lung cancer example. And here is down the bottom right hand side an example of a counterfactual question. So I'll read it out and then I'll unpick the different parts of it. So we've observed that somebody has cancer. So that's on the right hand side of the condition sign. We've C equals to true. So cancer is positive, is currently observed. We want to say, okay, given that context, what would have happened if we forced the patient to not smoke, or if they were forced to not smoke for a certain aspect of their life? In that new updated scenario, would they still have cancer? What's the probability that cancer would not be there? So given that they have cancer, what is the chance they wouldn't if they didn't smoke? And the kind of really crucial thing about counterfactuals is that the same variable can appear on the left and the right hand side of the conditional symbol. So it's weird here that we see cancer in both cases. And so this is kind of why these things look a bit strange, but actually they're kind of well defined. There's a good kind of sound complete logic underlying these types of questions. So how do we answer these questions? So here's a kind of slightly more clear-cut one. Given that I've observed someone smoke, so smoking equals true, and I've observed they have cancer, I want to ask, what's the probability they wouldn't have cancer had I forced them by intervening with the do operator to not smoke? And so Pearl gave a kind of 3-step procedure for how to compute these types of probabilities. So the first step is called abduction. What we do is there's some unobserved features going on in our model. What we want to do is update our knowledge of those given the observed evidence. So given we've observed someone smokes and has cancer, what's the updated belief about their kind of genetic precondition, for instance, in this case? The next step is fixing this new posterior distribution. I want to apply the do operator in this action step to reach into the model and force smoking to not be true. And then what I want to do is I want to kind of feed forward in this model. I want to sample from this new posterior, this updated distribution over the latents given the observed evidence, and feed forward this intervened variable for smoking. And in this model, I just want to compute what's the probability that someone has cancer. So given that these, the first two steps are true. So this three-step procedure, in a sense, demystifies this strange kind of distribution at the top, but cancer appearing on both sides of the conditional symbol. It's just a three-step procedure where you're changing the model in each one. And then the last step is we're just computing a standard probability in this updated and changed model. So this is very cool. So to give you an example to kind of see this in work, because I know that's a lot of kind of things to unpack there, I'm going to give you an example from medicine. So here in this example, what we have is we have a directed acyclic graph, a causal model, where we have these three different layers. So the first layer are what are called risk factors. So in this case, it's just being overweight. The next layer is talking about diseases. And the final layer at the bottom is all about symptoms. And so the kind of causal flows from risk factors to diseases to symptoms and so on. And in this case, what I want to compute is that given I've observed somebody has symptoms currently, would they not have the symptoms if I intervened and cured a specific disease? And so as we saw on the previous slide, the first step is we observe that somebody has these symptoms, so shortness of breath, chest pain. We now want to abduct, so update our model and update the distributions over all these things, given this new information, this observation. Then in this updated model, I'm going to do an intervention. I want to reach in and cure a specific kind of disease, which in this case is just angina. And then I want to, in this updated and intervene model, I just sample forward and I say, okay, I predict what happens to symptoms in this case. And you can see in this case, because angina is a cause of them, that affects the symptoms. One interesting thing is, had we intervened and cured diabetes, we would not have seen a change in the symptoms. And so counterfactuals really tell us something about diagnosis, right? What's the disease causing my symptoms? It's a counterfactual question. You can set it up in this way. So if you're interested in that, there's a kind of paper I had with some collaborators, my previous role that was in Nature Communications. If you're interested, you can go and kind of have a look at the finer details there. So we've talked about counterfactuals, we've talked about how to predict them, but as you might expect, as the causal model gets bigger and bigger and bigger and bigger, if we're conditioning on observed evidence and updating all the unobserved things in our model, this can get really computationally costly. So in this kind of DAG here with this 4 observed nodes, 4 unobserved nodes, if we're conditioning on some observed evidence and updating our knowledge about these unobserved latents, well, because we're conditioning, we're kind of introducing correlations in all these latents, and computing and updating and storing this kind of new distribution is really, really costly. And you can kind of see here as the size of the graph grows, it takes longer and longer to do this abduction step. So perhaps doing counterfactual inference isn't the most kind of computationally efficient thing you could do. And so to address this question, Pearl and some of his collaborators introduced what's called a twin network. So this was kind of in the early 90s to try and get around this problem, or at least to speed things up a little bit. So instead of just having a single graph, what we're going to do is we're going to graphically represent both the factual world and the counterfactual world. And so in the counterfactual world, the graph is just the exact same, it's just copied over. But what's happening here is the factual and the counterfactual world are linked based on these unobserved latents. And you might say, okay, well, why is it that this is what's linking these two different worlds? Well, the answer is if we're intervening in a model, we can only affect things within the model, because the latent things are telling us things outside of our model that we're unaware of. They're not influenced and they're kind of shared between both the factual and the counterfactual world. But what we want to ensure is that the preconditions, your makeup, your physiology, and so forth is the same in both worlds. And then given that information, I want to see what difference would it make if I change something that I can actually observe. So this is kind of what's going on here. And so how do I compute counterfactuals given this twin network? Well, it's actually quite cool, because in this case, if I just treat this twin network as a standard graph, counterfactual inference just reduces to standard probabilities. So this is kind of, perhaps strange, because in the kind of standard approach, we had to do abduction, update our knowledge, we had to intervene, then we had to predict. But what happens in the twin network is that we treat the counterfactual nodes and the factual nodes as kind of real entities. And we just want to ask, given something that we've observed in the factual world, what happens if we did something else in the counterfactual world? What's the probability that all these things happen? But this is just a standard kind of Bayesian inference task. And so in a sense, we've done away with this abduction step because we've reduced everything back to standard probabilities. So this is kind of the main difference between standard counterfactual inference and counterfactual inference based on a twin network. And so, in one, you do this updating step, you make changes and you predict. But in the twin network case, you just double everything. You do the interventions in the counterfactual world, and then you just predict. So you've gotten rid of that kind of abduction step. And indeed, it does kind of speed things up in this case, because you can kind of parallelize computations, you can take advantage of conditional independences and so forth. But what's really cool about this is that the twin networks provide this cool graphical structure. And if we want to use some type of machine learning algorithm to learn the functions and all this kind of thing, this graphical structure makes it really easy to do that, because it imposes constraints on the architecture of a neural network and so forth. And this makes everything really streamlined. So what does this look like? How do we compute counterfactuals using this twin network kind of idea? Well, the first step is we take our causal model, we translate it into a twin network. So in this case, we have some treatment X, some outcome Y, some observed confounders, which are Z, and then some unobserved noise term. And what we want to ask is an intervention about Y. So we build our twin network and we do that intervention an intervention about X. So we build our twin network by doubling things up. Then we do the intervention on X, which means that we drop the arrow going into X, which is what an intervention is. And then what we want to do is in this model, we want to compute the counterfactual. We've seen that it's just the same as doing standard Bayesian inference in this bigger or just computing probabilities on this bigger kind of causal graph. But what we can do is we can create a neural network whose architecture follows exactly this twin network in the second step, and then just train this model and use it to predict these probabilities. It's a kind of simple approach to computing counterfactuals where you don't have to do abduction and all this kind of stuff. And so the graphical nature of them makes them really amenable to deep learning. And the cool thing is that this yields a simple neural network that, when trained, will yield full causal models capable of counterfactual inference by just doing generating of probabilities on these kind of two outcomes at the end. So how do we train such a thing? It seems like a kind of strange thing, because we usually in kind of supervised machine learning, we have labels. So we have the outcome we care about. And like in kind of a regression model, we just want to find the function that maps some of the data points I care about to this outcome I care about. And so we have X and we have Y, but we don't have the counterfactual Y. What happens when X is intervened and then Y changes? So we need to, as a first step, find the correct outcome for that head of the neural network. Once we have that, we have everything, because we have the labels for the other head already. And so then we can just train this neural network and it can generate outcomes. So how do we do this? Well, the label that we care about is just the expected value of Y star, in this case, the counterfactual head, given I've observed some value of X star and some value of Z. Well, that's in the twin network. And as we saw with the kind of way to map between a twin network and a standard counterfactual case, this thing is just about the intervention on X. And there are various other models that already can compute such a thing. This is just something that lives at layer 2 of Pearl's causal hierarchy. It's just an intervention. So algorithms already exist that allow us to do that. So we use those algorithms to generate the outcome Y. That's our label for this kind of new approach. And then we train our model end to end with this new label. There's various other things you have to take into account, but I'm going to skip over them for the purposes of today's talk. If you're interested, I'll share the paper in a little bit and you can dive into the details kind of there. Okay, so given that we now have a way to kind of generate counterfactuals, what are the questions that we want to care about? So I'll introduce some notation first, which will kind of help us when talking about the counterfactual questions we care about. So I'm going to say Y with a subscript X, so big Y with a little X down here at the end, is the value of Y when we intervene with do X. So we force X to be a specific value. And that subscript on the Y is going to stand for this do operator. So now, using this notation, we can talk about some causal questions of interest. So we can talk about, given I've observed X is a certain value. So in this case, if X and Y are binary, if we observe X is equal to 1 and we observe Y is equal to 1, we want to ask what would have happened in that context if we had forced X to be 0. What's the probability Y would also be 0 in that context? And this thing is called the probability of necessity. And it's the probability that event Y would not have occurred without event X occurring, given that X and Y did in fact occur in the real world. So the fact that Y and X are binary here, what that just means is the event Y, which could be smoking or not, has occurred or not. This is why we're using binary kind of variables in this case. And we want to talk about, given that we saw one event happen and the other event happen, we want to ask, would that event still have happened if the other one didn't? What was it necessary to bring about the existence of a specific event? And this type of question is what's going to help us in the spring water problem I talked about a little bit earlier. So the first thing we got to ask is, can we identify these counterfactuals? So in the previous problem, we talked about disentangling causal interventions. We talked about identifiability, you know, what are the constraints in the model such that I can actually learn this? And you can ask the same question here for these counterfactuals. Do I need to impose extra constraints on my model in order to kind of correctly learn these distributions? And it turns out the answer is yes. And moreover, because this is another layer up the causal hierarchy, there's additional constraints we have to make. So just to give you a kind of really quick example, if we have a model where A is just causing B, there's no unobserved confounders, in this case, just A causes B. What's going on in this case, in this specific setup here, is there are kind of 3 parameters. So they come from the distribution over this latent noise term, which is affecting B. So B is just going to be either the same value of A, or it's going to disregard the value of A and just be 0 or 1, depending on the distribution over the U variable. So there's kind of 3 parameters in that. But when we look at just observations, which in this case are the same as interventions because there's no unobserved confounder, if we just look at observations, all we get are 2 parameters. So we don't uniquely constrain this model. And so there's 1 free parameter missing. And it turns out that this means that we can't identify counterfactuals, because the counterfactuals, when you look at the paper, you can kind of see that they're equivalent to this kind of extra parameter in this case. And so because it's not fully constrained by just the observations, we can't identify the counterfactual. So how do we do that? What extra constraints do we need to impose? Well, it turns out that in this case, in the case where you have binary variables, if you impose a certain constraint on the function that maps A to B on the previous slide, then in that case, you can identify what's going on. And the standard assumption is that this mapping is called monotonic. So it's kind of increasing. So as I increase the input, the output never decreases in a sense. And this came from work in epidemiology, where they kind of said that, you know, suppose there's a risk factor and a disease. And suppose now that if I observed that a risk factor wasn't there, but somebody had a disease, and I want to say, okay, would they still have the disease if they did have the risk factor? Well, the risk factor can only make it more likely that you have the disease. And so of course the answer is yes. And by doing this extra constraint, you know, imposing monotonicity, we reduce that extra parameter in our model. And so everything now, given monotonicity and our normal observations, we can identify all the parameters and then generate counterfactuals in a unique way. So that's the kind of difference between just interventions and counterfactuals. So the main thing is we have to, in our model, impose these constraints on the functions that our neural network is learning. And there's various ways to kind of do this given the architecture. You can also go from binary variables up to categorical variables. And in this case, we impose new constraints and we kind of dive into them in the kind of paper. But the main thing is this isn't just limited to binary variables. You can also talk about categorical variables. So the main difference here between layers 2, which is interventions, and layer 3, which are counterfactuals, is that at layer 2, we did have to make a constraint given the type of reasoning or inference we wanted to do to learn the correct model. But the kind of type of constraint we imposed was just on the way in which the variables themselves interacted to give rise to the answer. So we weren't saying any function is not possible. We were saying that, you know, in principle, any function that maps the treatments to the outcome is allowed, as long as any of the unobserved things are kind of outside of that function. But we need to impose more constraints in the counterfactual case, which is not just any function will do. We need to kind of limit the functions that go in there. And so that's the kind of, as we move up this causal hierarchy, because reasoning gets more and more nuanced, the learning ability gets more and more constrained in order to do the correct type of reasoning. And that's a kind of link between reasoning and learning in the context of Pearl's causal hierarchy. So now we have all this. If you want, you can dive into the paper and see kind of the actual details. They're kind of contained in the paper. But how do we now answer that question I posed at the start of the second half of today's talk? Should we protect these water springs or not? And so we're using our model and we're kind of generating these probabilities of necessity, probabilities of sufficiency, and so forth, asking the counterfactual question. So the counterfactual question we ask here is, given that the springs were protected and somebody drank from them and they did get diarrhea, what's the probability that if they hadn't drunk from a protected spring, would they still have gotten diarrhea? And so this is the probability of necessity we saw kind of a few slides ago. And what's interesting is this probability is really small for the data from this kind of Kenyan water experiment. And what this tells us is that actually, given that they drank from protected springs, they got diarrhea, would they still have gotten diarrhea had they drunk from a non-protected spring? The answer is yes. And so this tells us that it's not the intervention, not the kind of putting concrete around the springs that's kind of reducing diarrhea. It's something else. It's the intervention is not necessary. It's moreover, it's not necessary or sufficient to bring about the reduction that we saw. And so the question is, what could it be? And so this type of reasoning can't answer that specific question. But some suggestions are that perhaps the kind of educational campaign, when people were going into these villages and putting concrete around, people were learning, drinking from these things and not kind of treating the water is what's causing diarrhea. And so it was that intervention of the educational awareness rather than putting the concrete that possibly could have driven the average change in this thing. But what's interesting is you can use this type of kind of reasoning to kind of say, okay, this intervention that we want to scale up, is this necessary and sufficient to bring about the outcome that we care about? If the answer is no, then we need to go back to the drawing board and figure out what it is that caused the change that we saw so that we can really bring as much benefit to these types of things as possible. Okay, so the paper that I've been talking about with all the results of these deep twin networks and so forth is on the archive there. If people are interested, please dive in. When we kind of first announced it, we caught the attention of Judea Pearl, who first introduced twin networks. He loves Twitter, does Judea Pearl, but he kind of summarized it in a really cool way. So he was kind of quite fond of this paper, and the way he summarized it was kind of, to me, a really nice way of thinking about this work, which is that twin networks can now be seen in some sense as a computational engine. These can kind of really help us, or a computational instrument. These can help us in generating counterfactuals in real world situations. They're not just esoteric things to kind of think about counterfactuals in a way. They're computational instruments. So that to me was a kind of really cool thing. So again, one might ask, what's in this for Spotify, right? Why should Spotify care about generating counterfactuals in this way? Well, here are two examples. And again, there's kind of many more. But the first one is, what playlists should we update? So on Spotify, if you've ever kind of gone onto the homepage, there are lots of playlists recommended, and there are editors whose job it is to create these playlists, to curate them, to update them, to change songs on them and so forth, given how they're performing, how people are engaging with them. And you might ask, okay, for each editor, they have so many playlists to update. It's a really hard problem to figure out, which ones should be prioritized. So you can ask now, which playlists need to be updated. And by need here, what I mean is, I want to find the playlist that if it's not updated, people won't be engaged. But moreover, if it is updated, they will be engaged. So they're the ones that you need to intervene on now, because if you don't, bad things will happen. And so this, in a sense, is related to that medical problem that you might have heard about, where if you want to prioritize, let's say, ventilators, people with COVID, which people need the ventilator? Well, the people who need the ventilator are the one that if you give them the ventilator, they'll get better. But moreover, if you don't, they won't get better. So they need it to survive. And so this is kind of encapsulated in this counterfactual question here. And then there's another one, which is, new content that people might enjoy. So you might ask, if a specific user listened to a specific type of content and enjoyed it, which other content would they also have enjoyed? So given they saw certain content and engaged, what's the probability that a different type of content would keep them engaged, given that we know everything kind of in the background, the kind of variable Z here. So these two types of counterfactual questions are important for kind of what we're doing. And there are kind of many more in addition to that. So that kind of ends today's talk. So what we kind of saw was that there are, interesting causal inference problems that all need to be solved to address important problems, not just in kind of industry, but also in areas like, poverty action, healthcare, and kind of so on. And these problems, are still not solved. So there's many problems out there where, by looking at the type of data we have, type of questions we want to answer, new questions are coming up all the time, such as disentangling multiple treatments. There's also a range of counterfactual questions that yield kind of interesting insights beyond just averaged or heterogeneous treatment effects. And as we saw, deep twin networks provide kind of simple ways to use machine learning to learn these causal models and answer these types of counterfactual questions. So there are many more causal inference applications at Spotify beyond what we've discussed today. And I just want to say the kind of causal inference lab that we have there is currently hiring. So if you're interested in diving into any of these questions a bit more or applying them in the real world, please get in touch. My emails are kind of down there. You can also reach me on Twitter. So thank you all for your attention today. that's the end of my talk.
Thank you very much for this fascinating talk, Ciarán. We will move to the question and answer session now. We would love to hear audience people's comments and questions. Please enter your questions into the chat box or use the raise hand button to ask them yourself. You need to unmute yourself to ask your questions. I think in my view, your research is a kind of good example for the fact that studying causal reasoning is not only beneficial for academia, but to solve real world problems, which is impressive, Ciarán. Great. Stephen has a question. Stephen, could you unmute yourself?
Hey, hi there. Hi, Selma. I actually have two questions. One is clarification and one a little more substantial. First, let me say that that was a fabulous talk. The clarity of your presentation was remarkable. So my clarification question is, I didn't really understand the role of the deep learning machine. Why couldn't you just make the inference directly from the twin network?
So I guess the answer is the basic thing is to do it from the twin network, you need to learn the functions underlying it. So you need some way in which to do that. So not just the functions, but the distributions over kind of latent noise terms and so forth. And so in principle, you can use many ways to try and do that. So you could use standard regression in a sense. But the cool thing with neural networks in this case is that if you make their architecture mimic the twin network in a sense, and just find out what that extra label is, then you can just do it end to end like a standard supervised learning problem. And you learn the correct functions, and you kind of also have the nice ability to kind of add in extra constraints, such as these identifiability constraints, right? So there's simple ways from the literature of training neural networks that are monotonic or have other types of functional constraints. And so ultimately it just came down to, this gave us an easy way to do it. But ultimately any way of learning the function and the distribution can be then stuck into the twin network to learn or generate the right type of counterfactual.
So the idea is that you know the causal structure and you build that in to the learning network. You're so just learning the functional relations and the distributions of the variables.
Correct. Yeah. So you kind of know a priori what the causal structure is. So that's a kind of big assumption going into this, but standard causal inference algorithms usually make these types of assumptions. But the extra thing we're doing is we're learning the functions, but moreover, we're learning how to disentangle the function contribution to the output from the latent noise term attribution to the output, while imposing extra identifiability constraints on the actual function itself. So any way in which one could do that would be kind of reasonable. We just chose this way because of the kind of graphical nature of the thing, giving us kind of an architecture constraint on our neural network, and then just standard ML problem from there.
Right. Can I ask one more question? Hopefully it won't be too long. So these methods, as you know, you've made very clear, all make strict assumptions. Assumptions that, as far as I can tell, are not directly testable in any data set. So I'm wondering whether you have actually tested these counterfactual inferences or interventional inferences, whether it's even possible to do that.
Yeah, I mean, it's a great question. So to kind of jump onto the latter part, so the one about interventions. So there's a situation where in principle, we could check our answer, right? Because we could do a randomized control trial, see what the actual causal effect is and see how close we are to it if we just learn from observational data, so non-randomized data. And so we did do that in that paper. So we kind of had this kind of randomized control trial about treatments for a stroke. There are many kind of interventions that could have happened. They did two types of randomization. So one was they just randomized all of the kind of, you didn't get treatment or you got all the kind of treatments that we thought were applicable. And we trained our model from that kind of instance and wanted to see, could we learn the individual components? They did an extra randomized control trial where they gave each treatment separately. So they didn't do them all at once. And there we're able to show from just looking at the joint kind of intervention. So all of these dosages, let's say, at the same time, we're able to predict what the individual dosages, what those contributions were from that kind of randomized control trial, even though we didn't have access to that data at the time. So in that instance, we can check our answer. But now when we get to the counterfactual stage, here's a situation where we can't do it in principle, right? There's no way in which we can actually run this type of counterfactual experiment where we, in a sense, observe something, rewind time, change something, and then run time forward again. It's in principle not possible. There are certain counterfactuals which you can do it, but they're very kind of limited. So Pearl has a few papers about that. But so the question in this case is, how do we know we're computing the right thing? So one approach is to kind of say, okay, let's kind of build a synthetic data generation mechanism. So we say, this is exactly what the causal model is. This is the structure, this is the function. And then we just generate data from that model. And we give that data to our kind of algorithm, and then we train it and we say, generate a counterfactual. But now, because we know what the ground truth causal functions are, and now all this, we can generate counterfactuals ourselves that are the true counterfactuals, because we know everything we can know about the model because we created it. And we can then compare these two cases and see, do we actually get what we should get, in a sense? And there we kind of can do it. But if we want to talk about, in the real world, how can we know we've generated the right counterfactual? The answer is we can never know. There are certain situations where we might kind of get some intuition about, okay, I think we're doing the right thing here, because these identifiability constraints are the really important things. Because by just training a model on this observational data and asking it to generate counterfactuals, two models trained on the exact same data with just different training kind of methodologies, so different regularizers or whatever else, can in principle generate different counterfactuals. So you might ask, which model is the correct one? Well, in principle, both are correct, because they're both generating counterfactuals from the data they've seen. But where identifiability constraints come in is they kind of impose some sort of ground truth assumption about how the world works, to say one counterfactual is correct and the other is not. So this is where monotonicity comes in. So, it's kind of justified by this epidemiological kind of idea where, suppose risk factors always increase the likelihood of a disease, not decrease. And so if you generate a model from epidemiological data, which is like this kind of Kenyan Springs example, and you find that you're generating a counterfactual that's not consistent with a monotonic function, then you know it's the wrong one, because you know that monotonicity, or this kind of no prevention type epidemiological assumption, feels like it's been violated. And so while we can't say, okay, we've generated the right counterfactual, we can say the counterfactual we generated is consistent with things we know about the real world, such as monotonicity, or it's called no prevention in epidemiology. And the question then to generate to kind of from binary variables to categorical variables are, what reasonable assumptions can we impose on our model such that we can say this model is more correct than this model? And by correct here, I just mean, here's an assumption that I kind of want to believe in. If I've generated counterfactuals that aren't consistent with it, then I say that counterfactual is wrong. Although if I generate a counterfactual that is consistent with it, I kind of can't say it's the correct counterfactual. I can just say it's consistent with, let's say, domain knowledge in this case. So that's the kind of best you can hope for, in a sense, at the counterfactual level. But for interventions, you can check the answer is correct by running a randomized control trial.
Thank you.
Okay, shall we move to the next question?
I would also like to ask, I guess, two-part question about making assumptions. So my question is particularly focused on the first part of your talk about the assumption of noise terms being additive, unobserved noise terms being additive. I'm remembering that's correct, right? So I have two questions. One, to what extent do you think that is something reasonable to expect in pretty much any large system that most of us are interested in? Like, so for instance, if we are thinking about the application to this Spotify, I can just think about cases such as the location of the listener interacting with the time at which they are listening to music, or their emotional state, or whether they are listening it alone versus with many other people. So as the systems are getting larger and larger, we are also getting more and more different noise terms. And I would assume that it is making it much more likely that some of them will at least interact, and it's not going to be additive. So I was curious about your thoughts on that. Do you think that your assumption would actually in general hold?
So I guess this is it's a tricky question. Whenever you make assumptions, you kind of have to have some reasonable basis on which to kind of feel they're justified. You know, you can never prove them, right? But you can kind of say, I feel it's kind of intuitive. And in this case, it may not be, right? Because there may be interactions between these unobserved things. Well, the main thing is the unobserved things can interact, but the way in which they interact with Y is only through an additive kind of fashion. And so, you know, one question you might say is there can be lots of things out there, but we do observe them. So they're the kind of the C variable in the kind of node. So they could be things like, you know, how many songs did someone listen to yesterday? How have they been engaged over the last while, and kind of so forth and so on. And these things can interact, and moreover, they can interact with themselves, and they can interact with all the treatments and give rise to Y. So there's some sense in which we do allow for interactions, but the question is, how sensitive is the outcome of our model to the assumptions we put into it? So this is where what's called sensitivity analysis comes in. So we kind of say, okay, what happens if we break the assumption a little bit, right? What happens if we generate semi-synthetic data where we kind of sample from some sort of Gaussian or some sort of more complex variable in such a way that that thing is correlated with our treatment and our outcome, and stick it into our model, and moreover ensure that the way we stick it into our model is in a non-additive way. How big does the correlation between that thing and our treatment and our outcome have to be in order to completely skew our results? So perhaps to make a positive causal effect become negative, or perhaps to push us, you know, more than 1.5 standard deviations from where our answer originally was. And then you can kind of benchmark the sensitivity of your outcome to these kind of assumptions. You can kind of say, okay, well, the only way unobserved things can help when I'm kind of trying to understand what their distributions are and so forth, the only way they can help me in kind of predicting or getting better accuracy in my model is if all the observed things aren't really doing the job. And so it could be the case that you could observe loads and loads of things, which is the case at Spotify. And actually any extra accuracy kind of computation from the unobserved things is a little bit, but not a lot, such that if there are some interactions and so forth, they won't bias our results too much. And you can kind of get bounds on what this kind of, how strong the interaction has to be in order for, you know, our outcome to move in a certain way. And then you can kind of say, okay, given the setup and the problem I'm trying to answer and the data I have at hand, I'm not comfortable with those bounds. It's way too sensitive. Or you can say, actually, when I've done some kind of simulations on top, put in some unobserved things and made them interact in a way that I don't expect to kind of be the case in the real world, my outcome changes a bit, but not a lot. I have to introduce a lot of extra correlations in order to get a lot of movement. Then I say, okay, well, even though the assumption is probably not true in the real world, it's kind of, for all practical purposes, it's close to being true relative to my prediction accuracy. And then I can say, okay, I'm comfortable with how sensitive my output is, my model is to these assumptions that I baked into it. But of course, the issue with that is if you do this analysis and you find that it's really wildly varying, then you're like, okay, we can't do anything here, or we need to collect more data, we need to change our modeling approach and kind of so forth. So that's when then additional assumptions might kind of come in, and you can see what set of assumptions leads to the most robust or non-sensitive model to breaking those assumptions in a sense. But yeah, it's a challenging problem. Even like in standard causal inference, if you don't have the additive noise problem and so forth, it could be that there are unobserved confounders you haven't accounted for, and you just can't do that, right? Because you can't observe them. So in healthcare, it could be socioeconomic status. This could influence whether you take certain drugs, you can afford them. And moreover, it influences whether you get healthy quicker or not, because if you have high socioeconomic status, you can kind of afford good food, you've good diet, you can pay to go to the gym and kind of so forth. So your lifestyle is better. So perhaps you're more likely to recover regardless of treatment. But we can't observe that fact, right? Because it's not ethical. But you can use proxies to it. So you could use someone's postcode, for instance, to update your knowledge about what their SES is likely to be, and use that kind of proxy information to improve your estimate a little bit. So there's ways in which you can kind of get around these assumptions to various means. But the ultimate thing about causal inference as opposed to machine learning is that because you have to make these extra assumptions, you have to be really careful about checking that you feel comfortable doing sensitivity analysis with them, or simple ways you can kind of reduce how stringent the assumptions need to be. But it's a challenging thing that you always have to be cognizant about.
Right. Thanks a lot. well, the second part of my question was going to be, can you talk about what happens if those violations are, if those assumptions are violated and how much it deviates from the model? But you essentially just answered that before I even asked that. So that was great, thank you. And also I should say that even though I do think it's really important to talk about these assumptions and what happens when they are violated, I think this issue is true for pretty much any statistical model, even in simpler models. Like if you want to run an analysis of variance, you make assumptions about normality of the data. And we also know that it is often violated, but at the same time, we also know that violations do not create too much of a difference. So yeah, I guess want to say that even though I'd like to get comments about whether you think these assumptions are reasonable, I also agree that it is somewhat, it's not something that you can escape.
So I can kind of speak maybe a little bit to like how reasonable these assumptions might be. So there was this nice bit of work a while ago where people went out and collected lots of kind of what they call cause effect pair data. So examples, we had a cause and you had effect and you had the correlations between them. And they wanted to see, could they kind of, learn the causal effect? Could they estimate what way the arrow was going in these causal graphs? And what they did was they made this assumption of additive noise. And it turned out, because they knew what the ground truth was, because all of these examples were examples from physics or areas where they knew what the actual causal relationship was. So, one, for instance, was height above sea level and temperature at that point. So it's not the temperature that causes the height, it's the height that causes what temperature it is because you're further away from the earth and so forth. So we know there that, we know what the correct causal relationship is. But actually when you looked at the distribution over these different kind of cause effect pair points, is that a large number of them, so about, I think it's like 80 or something out of the 110 followed an additive noise model. So when you actually knew what all the variables were, but you just looked at the observed things, the change between how one predicted the other was additive. And so what they found in all these cases, because they were physically inspired and they came from the real world and so forth, that actually the additive noise assumption at some level is kind of a reasonable assumption. And the kind of justification they gave is because, like, if there's error in the way we're measuring things, so this error is what are the kind of like these latents that are outside our model. So the error is like the remaining variance about a variable that's not accounted for in its cause, let's say. But those things kind of come from us, the way in which we measure these variables in the first place. So like, if we have a certain type of weather instrument, then it's a little bit accurate. The way in which in physics and all these places we talk about errors, they are additive, at least on a small scale. And so if we're kind of talking about latent things and whether they're additive or not, in a large case, because the way in which we measure introduces error and the way the error comes is linear, the additive assumption is in some sense justified from that kind of point of view. So, in other cases like Spotify, you have loads and loads of variables, perhaps it's not as justified. But in many kind of real world scenarios that are relatively simple and all about kind of physics, the additivity assumption, you can kind of appeal to kind of measurement error and so forth as the reason for it being additive in those cases.
Right. Yeah, that's very insightful. Thank you. Also, a quick question. I guess a wild guess, but is this work that you've been talking about, is it from Frederick Eberhard, or do you remember where I done this work?
So the two papers that I presented here about work that I've done with some collaborators. The first one was kind of based on a previous paper where they looked at the opposite problem, where instead of looking at joint observations and disentangling to find the individual contributions, what they did was they look at individual interventions and say, when can just individual interventions tell us about what the joint intervention looks like? So that was work done by people from UCL. So Ricardo Silva and his, I think then master's student or PhD student did that work. The counterfactual, the previous work in counterfactual was from a long time ago, mainly by Judea Pearl, but there's a lot of people now getting interested in applying machine learning to counterfactuals and interventions and so forth. I have seen papers by him, but they weren't used in kind of this work.
Right, yeah, so when you mentioned like the physics examples, that's why I asked. Yeah,
Nice.
thank you.
Great. I wonder if there is another question. I think I can't see anyone raising a hand or any question in the chat box. Okay, shall we end the presentation then? Oh, thanks so much, Ciarán. It's very impressive, really very interesting talk. It's of course, it's amazing to see that, as I said, causal reasoning is just not a kind of topic for the